yesterday, Danning decided to summarize the conference proceedings so far with this meme, which is her mental model and a lot of people's mental model. She put economist. I think this is a better mental model for, I guess, crypto market design right now, which is take any problem that doesn't seem to be working, slap an auction on top of it, and say problem solved. Okay. And we know auctions work well, but we want to understand how well they work. So today I'm going to try and talk to you about a model of intents. I know you've gotten some, we got a bunch of stuff about intents yesterday, but let me just give you like the TLDR version. So here's sort of what I think about as DeFi V1. What was, back in the primordials too, what did life look like? And the way life looked like was there were all these very simple, like think of them as Uni V2 pools, maybe even Uni V3, but like just there were specific pools. And users want to do something, right? They want to take some ETH and trade it into USDC, or take some USDC and trade it into ETH. And what they're going to do is they're going to physically, personally go around, open various dApps, look at the prices, or use a command line and check the state. And they'll find a venue and a price that works for them. And when they find that venue and a price that works for them, they sign and send a transaction. So they could say, for instance, I'm willing to buy 1 ETH for up to 2,500 USDC. Like, obviously, these are not, I don't want you to think of them as limit orders. I mean like a standard sort of swap transaction, but you're specifying everything about it, what pool you're touching, so on and so forth. This isn't a great experience for the user. It really wasn't. The onus is on the user to find what it is. And then by the time the transaction lands in a block, that market may have moved. So their transaction may no longer be executable. The transaction may no longer be optimal, so they might have found a better price if they had used a different pool, but that was what you could do, okay? Second generation, as it were, came around and tried to address some of these issues, and what I'm thinking of are things like aggregator contracts and routers. And what these are just algorithmically sort of you're signing a trade order with another with another contract that is going to go and look for good fills for you. And there's a lot of varieties in the design, but it's still somewhat algorithmic. It's a single contract that's doing the work under the hood. And because it has to do that work under the hood, if you're on an expensive chain, it costs gas. Different aggregators have different amounts of what they look at, what pools they look at, what routes they consider, stuff like that, okay? So V3, where we're at, is over the last few years, people started thinking about these things called intent markets. And what they want to do is address these issues in a different way, and potentially, not in today's model, but sort of what they tell the venture capitalists is that they'll unlock other stuff too. But the basic idea is somewhat more sensible, which is users don't really care what venue they trade at per se. They care about what they get. So they have some underlying intent in most cases, which is, for instance, I want a ETH, and I want it for as low a price as possible. The intent markets are not going to try and solve for this on-chain. They're going to try and solve for this off-chain. So they're going to take this intent, hence the opening meme. They're going to take this intent and somehow try and shop it around to a collection of things they have different names for, solvers, fillers, essentially some form of market maker. And they're going to shop it around in many cases by an auction. So the solvers are somehow going to bid to fill these intents. The protocol is going to accept the best bid. There's a bunch of additional functionality this unlocks, but the basic idea is that the user just tells you what they want, the intent, and not worry about the details of how it gets filled. And the magic of the market, the auction, goes ahead and solves for everything else, all right? So 2 big examples, probably the 2 largest examples, CowSwap, which Andrea works for. I discuss it, I'm going to be nice to him, and hopefully he'll reciprocate. But CowSwap was an early example of this, because what it's essentially doing is it's taking user intents and it's batching them over time, trying to find, like, if there's a user who wants to buy wheat for USDC and another user who wants to sell wheat for USDC, maybe you can stick these 2 things together and satisfy both people's wants. Uniswap X, which is newer and sort of closer to the model you're going to see in the paper, is going to essentially take user intents, and then solvers are going to bid in a Dutch auction. So the price over time, the price is going to worsen for the user. And at any point, a solver can say, hey, stop, I'm ready to take it. What we're going to do is we're going to look at a simplified model of something like Uniswap X. What's our question? Well, our question is basically these models are, or the promises of intents are something like this: a large collection of very sophisticated solvers are for some reason going to compete to give you your best execution for pennies of profit relative to best price. And what that doesn't account for is that solvers themselves have to make a profit. They have to solve a costly entry or integration entry problem, an integration problem, and sort of effort, how much effort they put in to actually solve your particular intent. So we're going to consider a very simple model of an intent-based market and analyze the incentives of solvers under what we'll call costly and congestive entry. In particular, we'll show that if effort is congestive, then even with a large universe of potential solvers, with costly entry, even if there's a large universe of potential solvers, the market might only support a few. And if there is costly congestive effort needed to fill an intent, then you might be better off as the market designer actually having a permissioned market with a fewer number of entrants than the market will support. So you might get better, you might improve the quality of user outcomes by actually limiting competition. So that's going to be the punchline of the paper. For the next few minutes, I'll just show you. Yes, Bruno.
Makes sense to tax them and rebate that to the users, because if there's limited entry, they're going to make profits.
That's true. So yes, you're right. I have not solved for the optimal contracting. I'm just saying conditional on running an auction. There is a separate question of what is the best, because if you think of costly and like effort as some kind of principal agent problem, then really I have to solve a contracting problem, and it's not obvious that a auction is the best solution for that problem. We very conveniently leave that to future work on the last slide. Okay. All right. So that's the punchline. I hope that made sense. Okay. So what do we have? We have yes, sir.
What's the difference with this and CowSwap? Because
what's the difference between this?
Uniswap X, but
I don't mean to single out Uniswap X. My model is closest to Uniswap X in the sense that I'm going to look at one order at a time.
Okay, got
it. Okay. There is nothing about this. There is nothing about the results here. The economics of the results, the way an economist would say it, we could, we have the cow is a sphere problem in a different way, which is, I'm going to solve a very specific timing game, but I think the underlying mechanics would work for any intent market. Or even, I'll say that for now. Yeah,
Can I be a finance professor for a second?
Please.
What is the difference of the model that you have, which is DeFi-based, to a model of brokers?
That's, I mean, let me present the model, and then you can tell me what the difference is. I'm not a finance professor.
Andreas, try giving your order to multiple brokers.
Yeah. Okay, so what I have, by the way, is like really, my co-authors objected to this. I didn't update the slides. It's like, I literally mean a bog standard independent private values model, okay? So there's a single asset for sale. Think of it as like the right to fill a single intent, okay? There are going to be a bunch of people, solvers, potential solvers, and they are going to have a private value that is their value for the right to fill that intent. Think of it as, what is the best route I have found to solve that trade? Or what other sources of liquidity do I have? What is, if I'm holding on to inventory, what is my fair value for that inventory? Independent private value, independent of the independent private values may not be the best assumption on this. Maybe you want correlation of some sort because we're all looking at the same intent, but it is what it is for now. So the first model is a straightforward costly entry model. The solver, each solver draws a cost. That is their cost to enter the market. I'll denote that distribution by FC, but it's not going to do anything. Upon entering, they're going to learn their value for the object. So when you're choosing whether to integrate or not, or whether to be a part of this auction, you don't know what intent is going to be there or what the realized prices that you find are going to be. You just know that there's a distribution out there. You're going to bid in a first price seal bid auction. But we're in an IPv world, so revenue equivalence means the format doesn't matter. Okay? We could allow for a reserve price of R. That would just be like Uniswap X saying, if you, the solvers, can't beat the best on-chain price that we're seeing, we're just going to send it on-chain and we're not going to let it. So the first question we ask is how many solvers enter? And as might be expected, the more solvers in the market, the less an expected profit for any single solver. But the rate of convergence of this profit to zero depends on the tail of the distribution F. Okay? So for example, we show in the paper is out on archive. This is in recent days, this is one of the few times I've given a talk and the paper has already been up. So it is up on archive. Please feel free to take a look. I'm going to go easy on details for post-lunch purposes. For example, we show that if the value distribution is uniform, so it's a very thin tail distribution, obviously, then profits go to zero very quickly for any individual solver from entry. So the amount of entrants K as a function of the universe of potential solvers N goes to zero or the entry grows with the number of potential solvers at the rate N to the 1/3. As the tail gets heavier, for example, with an exponential distribution, the entry is like sort of square root N. And we have some fun little, we had a fun little side note writing this paper, discovering this thing called extreme spacing theory, which I didn't know existed before. But basically, we know from revenue equivalence that if K solvers enter, any solver's expected profit is proportional to the expected difference between the largest order statistic and the second largest, right? And extreme spacing theory tells you that you can make the differences between these two order statistics, the expectation of this as large as possible for as large as you want for arbitrarily heavy tail distributions. So for example, if F is Pareto with appropriate parameters so that the distribution is fat-tailed, we can show that you can support a large amount of entrants, okay? Note, you can think of thin-tailed distributions as representative of like blue chip tokens where everybody sees roughly the same price. There isn't a lot of variance. And fat-tailed distributions are long-tail tokens like obscure meme coins. One thing our model doesn't capture is volume of trades. Solvers are making one fixed cost entry decision, and we're sort of working on fixing that, but this has become a shirking paper at this point. So far, we assumed, for the second part, I have like 3 minutes, so let me go through this quickly. We assume that solvers only incur a fixed cost to enter the market and get their value for free. But in practice, finding a cost itself, finding a price itself, like finding how much you value the right to fill that particular intent at, is a costly enterprise. You need to search across various venues and routes to find the best way to fill that order, or you need to carry your own inventory to fill from, or stuff like that. You need to maintain a model then of what the fair value of your inventory is. So we're going to assume that each solver that chooses to enter puts in some effort level E. That effort level determines the distribution of values that they get. Cost of effort is going to be given by this function that depends on both the number of solvers in the market and the effort you put in. So your cost of effort could potentially go up if there is more, and if there are other people competing with you, maybe because you're all tripping over yourself to find the same source of liquidity to fill this order. Okay. So now how much effort is expended as a function of the entry decisions. We're going to show by example that total effort expended and therefore total user welfare can be better if there's a limited set of solvers. So our simple model, Shin, sorry, yes.
Intuitively, what is cost of effort in a DeFi setting?
So 2 costs of effort I can think of. One is I have to maintain inventories of meme coins. I have that maintain inventories of coins from filling from inventory. That's the cost, like carry cost that I have for carrying that, or the risk that I'm taking on, that is a cost that I have to bear. I can give you better fills if I'm holding on to inventory, but I have to, pay for it somewhere. Another would be like I have to pay for infrastructure that looks at that maintains, what is the current price on all on-chain things and looks for optimal splits. Okay, so
And that's effort or cost of effort?
That's cost of effort, and what I do, like the marginal cost. Sorry, that is, I'm describing either. So you can think of it as.
Oh, because one scales with the number of solvers, one doesn't.
Yeah, so like the second thing doesn't scale with the number of solvers. You could make a story where if all of us are tripping over each other, you and me are both competing solvers and we're tripping over each other to buy inventory, to be able to fill orders, then we're driving up the price of each other's inventory. But this, I have 1 minute. So this is a model. This is, all right. This is a masterclass in not managing your time. Okay, so simple model. The distribution of values that you have sort of increases in a first order stochastically dominant sense as you put in more effort. Cost of effort is just your usual economist's quadratic multiplied by something that depends on the number of other solvers. We can show, for this model, we have a nice analytic solution. We can show what the effort is. And this is useful because it says that if alpha k is linear in k, then the total effort that is put in by everyone in the, by all the solvers that have entered is constant. It doesn't matter how many people there are. But if instead alpha k is convex, then the total effort is decreasing in k. It's easy to show that user welfare is monotone, expected user welfare is monotone in the total effort that is being put in by all the solvers. So if you buy this assumption, then you conclude that user welfare is better off with fewer actual solvers in the market. All right, so this is what I did. I'm out of time. This is my meme to contribute to Danning's meme. All right, so stop now.
Right, so the discussant is someone who deals with the intent-based markets on a daily basis.
All right. Yeah, so thank you very much. Oh, first, just one small thing. I realized earlier that I sent not the latest version of my slides by mistake, so my slides are a bit messy, but okay. I think I can do my discussion. So, well, thanks a lot to organizer for asking me to give my comments on this paper that I very much enjoyed reading. And actually, let me just say that I think one of the biggest problem with the paper and the presentation is that I think these guys don't do enough into justifying why those things are important. Okay, I may be a bit biased here because obviously I spend all my time looking at these objects. So I think they're great. They're super interesting. They're super exciting. And I think they should say it more. But for example, this intent auction intermediate between 5 and 6 billion US dollar per month. So they are quantitatively relevant. They solve some of the big problem on that we discussed yesterday, for example, MEV, because you are pushing the risk of sandwiching and so on the shoulder of solvers that are supposed to be the professional. They solve a lot of issue with liquidity fragmentation. This, was mentioned in the introduction. I think, there's more to explain why do we need to study them. Okay, so first point. And okay, the expectation is also with other form of fragmentation, cross-chain, and so on and so forth. This will become even more important. Okay. So let me give it's customary to give a high-level summary. So my personal summary of the paper is that there is a 3-step analysis. The first one is to put down a sort of benchmark in which there is this intent auction with no entry cost and no effort. And this is very very plain vanilla auction in which solvers just draw a price and then they decide how much to bid. Okay. And this is sort of a benchmark because then all solvers enter, and this is somewhat maximally beneficial to the users. In the paper, there is something about optimal and all that, but of course, technically to optimal auction, you need also a reservation price and other things, and aren't really discussed. So let me just say that this is maximally beneficial given the reservation price that it's kind of P star in the paper. Now, the next step is to introduce an entry cost. And okay, if we leave aside distribution with super fat tails, which is a little unrealistic, then essentially entry cost reduce enter. And here the paper does a good job at characterizing exactly how much given a possible distribution of types. And finally, the last step is introducing costly and congesting effort that in the paper is justified by saying that so essentially by claiming that solvers need to have inventory, and carrying this inventory has a cost. And it's congestive because, of course, if all solvers need to carry this inventory, then it's become more costly for everybody to actually have this inventory. And the result is that if all the entrants have to carry inventory in an intent market, then the existence of other entrants drives up the cost of sourcing and carrying the inventory, okay? Now, then it turns out they have the result where, okay, forget about this question mark. Under some condition, you have that actually having fewer solvers is better because of this negative externality that they impose on each other. And here just a little note, because you seem not to have really closed the argument, because the number of solver entering is an endogenous variable. So what you probably want to show is that under some condition, if you increase the cost, then you actually, this is better for the user. Which leads me to one of the comments that ended up later in the discussion, which the way you set up the analysis makes it looks like the cost of effort is kind of a design choice, because, hey, look, you know, on the superficial level, if I have it, it's kind of bad, but then if I make the model a bit more complicated, it might actually be good. But you never really say it or treat it as if it's really a design choice. And so this is first question, like, because if it's just kind of, it exists, period, this technology, we cannot do anything about it, then it's one thing, or if you think this can be changed or chosen by the designer, it's another. Right, so my take on the paper, yeah, as I said, okay, perhaps because I wouldn't spend most of my day looking at trading intent auction if I didn't think this is an important object. And so therefore, I find the paper very relevant because it studies a very important topic. It has a nice and novel intuition. I mean, again, despite the fact that I spend all my day looking at this auction, I learned from this paper that there might be this kind of negative externality that solvers impose on each other, and I think it makes a lot of sense. However, I think the paper has several loose ends that would be nice to tie them and to make it more robust. The first is on the modeling choice, and I'll argue in a second that the model assumes that all effort is congestive, but in fact, there are many ways to be solvers. There are many ways to invest into making your, and some of them aren't at least congestive the way I can see this. And then, okay, the mathematical derivation, I had really a bit of difficulties following them. I think there is a kind of innocuous mistake in the paper in the sense that profits can be negative sometimes, and this should be kind of truncated. I mean, I don't think it matters too much, but more in general, I had difficulty following. And okay, I probably won't have time to discuss it, but while I was reading the paper, I just made a point of writing down as a kind of first read a bunch of questions that came to my mind. And for example, the first equation, I think it took me quite like a good half an hour to understand what it does. And if it's the first equation is half an hour, it sort of discourages the reader from moving faster.
It's the cost of entry.
It's the cost of entry, effort. Yeah. And so that's it. So I think it would be quite worthwhile to make the modeling a little bit more, how can I say, nuanced. So let's start. I think the main result we should survive because they're intuitive enough, but with additional interest result probably. And then obviously as the derivation become more transparent, I think the paper can then have a higher impact because you understand better what's going on, can build on top of it, and in general you reach more people. Okay, so as I said, the main assumption is that there is this congestive effort, which is justified by saying that solvers need to hold the inventory. And this is from the documentation of Uniswap X. And I don't know if you can see it, but essentially it says the simplest field strategy, so the simplest way in which solvers can participate in the auction, is called direct filler, where the trade is executed directly against tokens held in the filler address. This is exactly the strategy that the paper focuses on, where you hold assets in your address, and then this is how you participate in the auction. However, more sophisticated fillers can implement arbitrary complex strategies by deploying their own execution contract, blah, 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 blah. And then they can specify arbitrary callback data. So I'm just bringing it up because the callback data is essentially you participate in the auction by specifying how you will access. So you tell the transaction that you would execute if you were to win the auction. And this essentially allows you to participate in the auction by tapping on existing publicly available liquidity, where the name of the game, if you decide to go this route, is to like set up a optimization algorithm that allows you to split trades, use intermediate assets, whatever you want to do, so to get the best possible price. So there are at least these two strategies. Okay, then you may say, okay, this is the documentation. Maybe nobody does this second thing, and it's all in the first type of strategy. But okay, this instead jump to cow protocol. This is data from that Arakis put up actually a couple of days ago. It was interesting to see, where essentially they look at well, cow protocol and only ETH USDC pair, which is the token pair most likely to be filled using private inventory, because nobody wants to hold meme token. But here people are happy to hold it, so it's more likely that it's used this way. And even you don't see, but this gray area here is filled using units of V3. The lighter gray is filled using other DEXs or cow, so other liquidity on cow swap batch. And the rest are various type of private market maker or RFQ systems. And okay, yeah, maybe most day the majority of volume is filled using private market makers. But still, you can compete in this auction by instead choosing the other strategy, the one of optimizing, you see. And some days, actually, almost half is filled in this way, some other. So the point is that, to me, you are kind of assuming a way, perhaps some very interesting research question that you could tackle with the framework that you've already developed. First one is that, as I said, solvers can, but don't have to, use their own inventory to participate in the auction. And the question, very interesting, would be, when do they want to do it? Because again, if the idea is that they impose a negative externality, then perhaps they choose too often this strategy, because of course they don't care about what they impose on the other solvers. So anyway, there can be something interesting to say about that. And then also not completely obvious, and I think even if you don't change the model, to be worthwhile discussing, just the fact that you want to participate into the auction by using your own inventory, to me, doesn't necessarily immediately imply that there is a negative externality on the other. How? Because you could, for example, do it by using liquidity that is otherwise idle. Like, you just kind of, people are happy to sit on ETH for no reason, and then you tell them, look, how about I give you some money and then I use that. So it feels like if you are assuming that this liquidity is coming from public, for example, AMMs, in which case it's the same source for everybody, in which case you have this kind of congestion. And again, it would be interesting to think more carefully and perhaps even model the choice of where to get this liquidity if you want to participate into the auction by holding inventories. Okay. 2 minutes. Okay. But my difficulties with the math, let me just, okay, this we can discuss later, the details. But yeah, I mean, there are statements and then equations, and it's kind of hard to feel how from the statement you go to the equation. So this, for example, this equation, the argument is that it follows from the revenue equivalent theorem. Revenue equivalence theorem is one of those theorems that, there are many versions. It was discovered, I think, the first version by Vickrey, and then many variations. So there's no one unique statement. And in the proof of the then after a while, I remember that in the proof of the revenue equivalence theorem, there is a step where you use the envelope theorem to derive the optimal. And then I kind of, that's what they are doing. But in some sense, you impose quite a bit of a burden on your reader that they have to remember line 2 of the proof of the theorem, not the statement, line 2 of the proof, to understand where this equation comes from. And so, and plus, as I said, this equation allows for profits to be negative. And so it's probably missing some piece. And that's why it would be good to see the derivation. Okay. Additional comments. I think I mentioned most of these things. Let me just say that, yeah, kind of, a lot of the discussion is about how these fixed costs reduce competition and reduce welfare. And the question here, just as a way to also think about the paper more broadly, is with respect to what? Because clearly, if the only only type of auction we can design is one with costs. Then the question, okay, well, it's still an improvement relative to the case of no auction, so we are happy about that. But if we think of this cost as something that we can manipulate, change, work in, then yeah, then becomes it's a different discussion.
And with effort, it's not an optimal. I mean, we don't know what the optimal auction is. I don't know.
Yeah, so this was also my last point, like optimal when it comes to auction, there is reservation price, effort, yeah, it's a bit unclear. Also, why effort? This seems to be a variable cost to me. I mean, it's all like cost that you have to bear before you enter the auction. So, because that was a bit confusing. Anyway.
Sounds like a Milgram or hazard team problem, and we have externalities. Armstrong.
It's more of a tournament because there is one winner in the end. Okay, but this is all right. Anyway, yes. Thanks.
No, thanks for the comments. And yeah, we focused on the case but points are well taken. We just focused on the surprising result, but you're totally right that there's also design, and there is we do understand that there are other ways to be a solver that's not that don't require relying on your own liquidity. It's just that's where you get the interesting results, so we focused on it. But you pointed to a different interesting direction we could go, so we will.
Can you please explain again why there is this externality in the effort? I did not understand. Maybe you can give an example in which this is the case.
So there's 5 of us who all want to fill from liquidity, from our personal liquidity.
Yes.
We all have to then go and buy that token in advance to have it's not a great example, but it's one. So yeah.
I have a related question. So if the solvers have to hold inventory, then I can see why there is negative externality because they're kind of bidding for the same inventory assets. But then if you're relying on on-chain liquidity as a case of as a default.
And that was his point, and I think his point, which is that there are versions where if it's just we're all competing by searching on chain and not providing new liquidity sources, then the liquidity there is still an effort choice problem, but you don't expect there to be a cost of
there's no externality.
No,
but you get an equilibrium between the on-chain liquidity and the optimal solver.
I mean, we don't have we could work it out, but you have to add a little more to the model. Siamak pointed out very graciously that there are other reasons in TradFi where you want to limit, and there the externalities are normally informational externalities. Yeah. So someone might, if you're just information leaking to too many brokers, but you want to go away from an IPV model into a common values model for that, for some of that.
And if there is this externality, and so it's better to have many bidders, then maybe it becomes a design issue. Okay, you're going to be the only bidder, but we are going to tax you and rebate part of your profits to the user.
We already have that. It's called Robinhood, right?
Yeah.
We just, depending on which audience you're in, they don't like it or they do like it. But yeah, no, that's exactly right. Like I said, we haven't solved for that design question, because you can then do Curti Lee style you can do an ex ante payment followed by an ex post auction, right? So yeah.
All right, so let's thank Mallesh and Andrea.